Okay. We would like to keep this interactive, please, because the one-way lecture thing gets boring after a while, even for me. Are you all from the Maths Club or invited by the Maths Club? Invited by? Okay, good. Um, what backgrounds are people from? Can I just see like maths? Just raise your hand. Okay, quite a few. Physics. All right. Chemistry. Chemistry, no one. Biology, or I don't know what other disciplines you have. Okay, earth sciences, apparently we have some. All right. Okay. Um, so we'll start the session in a minute or two. I hope you can all be in a place where you can see one screen at least. Um, if you want to follow the code hands-on, we will share the things. Okay. So just introducing ourselves. So my name is Dhruv. I work with the MathWorks education team based out of New Delhi. With me is my colleague Nikhil. He's based out of Pune, same education team. So what we do is we work with educational institutes, professors, researchers like yourselves, and we basically try to help as far as possible in scientific computing and model-based design. Okay. Um, how many of you are already familiar with MATLAB? Can I just see a show of hands? Okay. Is anyone using any alternate, like you might have used Fortran or NumPy or anything like that? Okay. Is there anyone who is totally new to scientific computing? A few people. Okay. That's all right. That's okay. So this is intended to be a 2-day workshop. It's an introductory session on how to get started with scientific computing. So we will not cover, the whole spectrum of everything like loading data and plotting and machine learning and all that. This is basically about how to solve equations and how to create models from which you can get some actionable results. All right. Uh, yeah, I think we have a full house, so we can now start. Nikhil, do you want to introduce yourself?
Hi everyone. So as Dhruv mentioned, I work with the same team as Dhruv. We work with educational institutes, researchers, and students just like you to help them with their research and curriculum for professors. I have completed my master's in biomedical engineering from IIT Bombay, prior to which I completed my bachelor's in electronics and telecommunication. And as I mentioned, we support tier one universities across the region. And I have been using MATLAB since about more than 10 years now. So there we have some knowledge of MATLAB, and then we have entered into this particular job profile. So if we will try to help you with all your queries that you have today, and let's make this particular session a fruitful session for every one of you.
Thanks, Nikhil. My background, just very briefly, I hope the audio is not working here. So I used to work on this thing. What you see on the screen is a wave energy converter. So this is a device that we used to deploy in the middle of the ocean. And we tried to capture the energy within the oscillations of ocean surface waves. So I come from a mechatronics background. And all the stuff that we're going to use today, I mean, differential equations, technical computing, modeling, design, all of this is actually useful in the real world. So if at some point you consider converting your research into application-oriented, products, all this stuff does come in very handy because what we want to do is to be able to design real-world devices that are cheap, that work properly, and that design and that work as per the design. Okay. Not spending too long on ourselves. If any of you've used MATLAB and Simulink, these are the tools we make. They are used in a lot of industry as well. So especially if you look at aerospace or automotive or communications industry, these tools are the industry standard. The reason we engage in education is to make sure you have the training that's needed for when you want to transition to industry, or even in higher education, we use a lot of this stuff. All right. Now, I hope everyone has been able to create a MathWorks account. Is there anyone who needs help with that? Just raise your hand. Do you all know how to make an account? Yeah. Okay. I'll just quickly show you just in case there's anyone who doesn't know. So what you do is you open any browser and you can type this thing, IISER Bhopal MATLAB portal. Okay. When you type that, the first link that will come up will say IISER Bhopal. And when you go to this page, this is a portal where if you scroll down a little bit, there will be this blue button, sign in to get started. If you haven't made your account, you just click on the blue button, sign in with your official email ID. That will be iser.ac.in. And then you will get automatically associated to the license that your institute has purchased. Okay. So you will get access to all the products, and you can also use MATLAB online straight from the browser after that. In case anyone needs help with that, just let us know. We'll come around and help you. For the people who just walked in, can you please go to this link? Okay, the URL is on the screen. If you go to this link, you will get access to all the workshop files that we're using today and tomorrow. So it's tinyurl.com / IISER Bhopal Math. So when you open this link in the browser, what you will see is a page that looks like this. Okay. I think the screen has some weird artifacts, just ignore that. So you will see a folder that contains some subfolders and some more files. There are two options. If you want to use MATLAB online, what you do is you click on the drop down arrow next to My Files and click Copy Folder. Okay. Do not add a shortcut, because if you add a shortcut, you will not be able to modify the files. You will have read-only access. So if you copy the folder, you will get those files and you can make changes. If you're working on a desktop version, you use this link, download shared folder, and you can download all the scripts. Anyone need help with any of this? Okay, just raise your hands. Don't be shy. Like we're actually here to help. This is not a test.
How many of you are using online versions of MATLAB?
Okay, about half.
Oh.
Okay, so we have tested these scripts in the desktop version primarily. They should work. In case they don't, we'll figure something out. All right. We have an agenda slide. Just 1 second. Okay. So this is the agenda that we have planned for 2 days. So we have about 3 hours or so today and 3 hours tomorrow. I hope all this was shared with you. So hopefully you're in the right session. So today what we're going to look at is how to get started with MATLAB live scripts, including putting in equations using LaTeX formatting. Then we're going to look at how to solve ordinary equations. And we're going to focus a lot on solvers, like how to write your own solvers to solve equations. So we look at things like Euler method, Runge-Kutta method, variable step solvers, stiff solvers, etc. If we have time today, we'll also show you a little bit on discrete Fourier transforms and frequency domain methods. Otherwise, we might shift it to tomorrow. Let's see. And tomorrow, then we'll look at partial differential equations, which are typically more than in one dimension. And we'll look at how to visualize these things in 3 dimensions, make animations, how to choose step sizes, how to choose mesh sizes, and also some efficient programming methods, like how to vectorize and parallelize your code. I hope everyone is in the right session. And assuming you're still here, like you're interested in this stuff. Is there anything else anyone would like to learn just at the beginning? This is all what you were expecting, right? A little bit about Simulink. Okay. We'll try. Let's see what speed we can move at. So Simulink is definitely useful for ordinary differential equations. It's what I prefer to use personally. But we didn't plan it for the agenda, so we'll see. If we have time, we'll fit it in somewhere. Anybody else? Is there anything you were expecting to see that's not on this list? Yes, no? Okay. Just let me understand your backgrounds also a little bit. So have all of you taken a course in numerical methods somewhere in your education at bachelor's or master's level? Not really? Okay. I'm just looking around the room to get an idea, because if you have not, this will be very, very useful to you, but we will need to focus and kind of pay attention consistently. Okay. All right. Okay, let's get started then. So I hope all of you have been able to get access to the files. I'll just copy this folder to my MATLAB online as well and just show you what the interface should look like. And then we'll get started with some scripts. So if you've copied the folder properly, it should, when you open MATLAB online, so that's just matlab.mathworks.com. Depending on the speed of your Wi-Fi, this might take a while, but you should be able to see the folder in your MATLAB drive. So if you're using MATLAB online, you should see a folder on the left-hand side in the file browser that says IISER Bhopal. Is everyone able to see this who is using online version? If anyone has any issues, please raise your hands. We'll come around and help. Is everyone able to see this? No? Anyone else? Are you guys able to see this? There? That table? You have issues? Okay, I'll come in a minute. You guys are able to see this? That one? Okay. Okay, I'll come and help you. Anyone else? All right. Yeah, just please help out your neighbors as far as possible, because we want to be collaborative. So I just come around and look at the issues. Who else was stuck? Who else found the topics? Just help each other. Who else needed help? That. Who else needed help? Yeah, just zoom out a little bit. I think people still need the files. Okay, all of you, when we ask questions, if you need help, please raise your hand. Okay. This is not a test. Like, we are here to help you. We want to help you. So help us help you. So if anyone needs the files, just go to this link, tinyurl.com/IISER Bhopal math. That MATLAB drive interface will open up. Either copy the folder or download the files, and you will have access to everything. Okay. It is here. Okay, so if you have copied the folder successfully in MATLAB online, on the left hand side, you will see a folder that is called IISER Bhopal. Okay, you just double click on the folder. Inside, you will see a list of all the files. So that's all that's needed. And those who have figured it out, just help your neighbors. It will make the whole thing much smoother. Who else needs help? Okay. How large is the download? What? 3.7 GB. It's 50 MB or so or something. Okay, does anybody else need help? Or you're stuck or you don't know what's going on? Okay, so I think some people are just downloading the files. That's okay. I'll show you what to do once you have downloaded the folder. So after you download the folder, just unzip those files in some location that you know. Okay. And then you can open up your desktop copy of MATLAB, those who are downloading the files. So that interface looks like what you're seeing on the screen. Right? What you have to do is you have to go to this bar up here. This is the address bar. Just click that button which says browse for folder. Okay. So after you have downloaded and unzipped the files, you just browse for folder. Go to the correct folder, which should have a name like IISER Bhopal. Okay. And then just hit select folder. And then all of these files should appear in the file browser on the left hand side. Okay. So if you can see these files on the left hand side of your MATLAB window, then you're good to go beyond that point. You may or may not have the slides, that's okay. Just the folders you should have. So I'll just come around for a last check, then we'll start the hands-on part. What was it? So laptop has larger into the tree. Just try as well also. Forward. Any issues? Fine. Okay, does anybody else need help with anything?
Even yet to have access to the file.
I think you can start probably. People are very it's not that easy. Yeah, right. All right, I think some people need some time, so let us show you a little bit of like playful, fun stuff before we get to the serious things. So why should we care about numerical computing and what can it do for you? Okay, that's why we are all here for these 2 days, right? Is anyone here using numerical computing for anything that they would like to share the application? Do you know what numerical computing is for? No? Has anyone used numerical computing? Just okay. What do you want to just share a couple of sentences?
A very advanced thing like cosmolatics. Okay. So it's used for this time evolution of universe.
Okay, that's okay. So you have created or you're using some kind of mathematical model of the universe to predict how it's expanding or model how it's expanding. Okay. Okay, so you have all learned maths, at least in your classes, right? You've learned differential equations. Do you know why that stuff matters in the real world? Okay, let me show you a few kind of examples, and then we'll see, how to solve some real problems. So inside this folder that you have, there is this package called numerical computing with MATLAB. This was actually written by the person who created MATLAB. It's a mathematician called Cleve Moller. If you double click on this package, it will install this as an app on your copy of MATLAB. I'm not sure if it works on the online version, but it will definitely work on the desktop version. Okay. So if you double click on this and install the app and go on the apps ribbon, this package will appear here. That says numerical computing with MATLAB. And if you open this, it will show you some interesting kind of applications. So let's just spend like a couple of minutes on this before we solve our problems. Okay, I'll just open one of the apps from here. So you can see this thing kind of moving on the screen. Can anyone tell me what this is? What does that look like? Okay, you all have to be interactive, otherwise this is going to get very boring very soon. What's that on the screen? It's not a trick question, guys. Stick figure of a human being. Okay, is it moving in a realistic way? Yeah, kind of. Okay. So what you will see on the bottom of the screen are some sliders. And through this, we can change how that human being is walking. So this is a mathematical model of the biomechanics of the human skeleton. And this is the kind of thing that people study using numerical computing. So let's look at some of the stuff we can do. Suppose I increase the speed slider here. Okay, that human being appears to move a bit faster. But of course, it's not a human being. It's just, I think, 21 points on the screen. And there's some frequency of motion underlying those points, which are giving the illusion of movement there. Similarly, if I increase the stride length, okay, you will see it starts taking much longer steps. It's a very, very simple model. Now, if I had to get a real live human to do this, it's actually very difficult to get data for research because you have to get a human being, you have to get their time, you have to get the medical permissions, you have to put sensors all over them, and then start recording data. But if you have mathematical models, you can create a simple, representation of what a human movement is like, and then you can play around with it and discover various sorts of things. Okay, let's look at this thing. So the last one, the last bar here is called gender. So this kind of changes the profile of the movement. Just guess what's happening here. So I'll take it to one extreme. What does that look like? Ramp model, someone said. Yeah, so that's what happens when someone has wider hips actually, because that represents a somewhat more feminine kind of motion. Let's take it to the other extreme. So I'm going to reduce this all the way to 0. What does that look like? Yeah. These are just some points on the screen, but you can tell what's happening, right? So this is what happens when your weight is more towards your shoulders and you're walking with a very heavier gait. So much more masculine kind of motion here. Let's make it a little bit more neutral. Let's try adding a bit of bounce here. Okay, that didn't do that much. Or we can add some hopping motions. If I reduce the stride length, it will look different. Okay, you can see that person is kind of putting a little bit too much load on their knees in that way. All right. So this is a very simple model that's known as an eigenwalker. Has everyone studied eigenvalues here in matrices? Okay. So this is known as an eigenwalker model of a human. And just by taking the eigenvalues of the motions of certain key points on the body, you can simulate how someone is walking, and you can discover all sorts of interesting things. So this is just a fun kind of thing that we can look at. So I'm going to stop it now. There's lots of demos in that app you can look at. All right. Uh, Let me show you one thing about waves. So what does that look like? Some kind of waves, static waves, standing waves. Okay. If any of you are from a physics background, like waves are the fundamental building blocks of everything you do, right? In quantum mechanics, in electromagnetics, all sorts of places. My PhD was in something very similar, like modeling waves because you want to capture the energy. If you're working in different kinds of domains, waves are one of the things that show up. Okay, so you can model waves. This stuff is quite easy to do analytically, but suddenly when you get to two-dimensional waves, it becomes a little bit tougher. So let's go to, let's say, waves on a square domain. And I'll slow this a little bit. What does this one look like? It's like someone bouncing on a trampoline, right? So as a matter of fact, this is what happens when you have liquid flowing through some kind of square surface. Okay. And the foundations of MATLAB are very deeply connected with this problem, because if I change the shape of this to a L-shaped domain, okay, this is a very special kind of problem. I'll just focus on the first one here. So this is the first solution. The rest are higher order solutions. This might look familiar to some of you. Can anyone recognize this? Okay, I'll give you a hint. Just look at where my cursor is. Can you see that shape? Yeah, so that's actually where the logo of MATLAB comes from. So as it turns out, that if you try to solve the wave equation on an L-shaped domain, this is something that came from a real problem. I'll show you a picture in a minute. This is something that came from a real problem in hydraulics. And the person who invented MATLAB was working on a PhD thesis trying to solve this equation on an L-shaped domain where you have a cutout. And what he discovered is that through analytical methods, that's the maths you study in your classroom, there's actually no way to solve that equation. Okay, because analytical methods work when you can fit some sort of idealized solution. So what he ended up doing is he ended up writing a lot of code to be able to solve problems in that kind of meshed domain. Those those cross lines you can see is called as a mesh. And that was the kind of birth of MATLAB. And since then, MATLAB has been used to solve lots of different problems which don't have analytical solutions. If you can write the equations, if you can write the boundary conditions of those equations, your computer can crunch through the numbers and try to figure out what the solutions should look like. So I can just show the backstory of this. Oops. So if I just type MATLAB logo story, what we will discover is the MathWorks logo is an eigenfunction of the wave equation when it's solved in an L-shaped domain. There's a whole story on this. You can read this article if you're interested. I'll show you what physical problem this was used for. Okay, so if it's this kind of component and some liquid has to flow through this hole over here in the middle, if that liquid is going through some vibrations and you try to mathematically find out what that looks like, you can't do it using analytical techniques. If you look carefully, the 1/4 of that is an L shape. Okay. So the first version of MATLAB was created to solve this problem, the quarter plate kind of problem. And that shape that you've seen where the wave is kind of standing up, that's where the logo of MATLAB came from. And this stuff is used all over the place now in all those different industries that we mentioned. So over time, we'll try to show you how you can use numerical computing by focusing on some simple problems and helping you write code that you can use to solve the specific problems that you're working on. Okay. I hope this stuff is kind of interesting to people. I can't honestly tell because like people are quiet today. All right. Does everyone have the files now? Okay. Should we get started with the hands-on part? Yes, no? Where's my colleague gone? I lost him. Do you want to start with the hands-on bit? If anyone needs help, just raise your hand. I'll come in.
Am I audible? So with that background, just about understanding where we are going to implement or what are the possible applications where numerical computation is being done, what we'll do is we'll try to take some simple problem that we have studied or we have experienced in our day-to-day life, and we'll try to see how we are trying to solve that particular problem. Okay. So now I will be talking about, we'll actually discuss more on the ordinary differential equations, what exactly are our ordinary differential equations, how we try to solve them, and so on. But before we get into some problem, can someone tell me what exactly do you mean by ordinary differential equations? We generally call them as ODE. What exactly is an ODE? Anyone?
Only one variable.
Okay, only one variable. And y equal to x. Y is the response. X is the other variable that we are looking into. Is this a differential equation? Sorry.
It's just equation.
Yeah.
It's not a differential
Okay.
equation. Which
Okay,
we have a
going towards
differentiation with respect to a variable.
Okay.
Only single variable.
Okay. Yeah. So basically, it's a differential equation, as the name suggests, with one variable that we generally call as ordinary differential equation. Okay. Now, depending on how complex it is and how what is the order of it, the entire complexity of the problem varies. Uh, so what I'll do is I'll open an example. So if you go into the ODE folder, I'll be accessing the ML01 symbolic uh, file.
Just make sure you double click on the folder to go inside because that will get the files on the correct path.
So before we start with something, before we start solving ODEs, what I will do is we'll take some we'll try to solve that particular basic equation kind of a thing, as one of our colleagues mentioned. So anyone knows what exactly are symbolic variables? Is there for? Okay, there to represent something, but can you polish it a bit? Yeah. Exactly. So it doesn't have a value attached to it. The value can change. So in an equation, when we say y equal to x, these can be symbolic variables where depending on the change of value of y, the value of y, depending on the change of value of x, y will be changing. Okay, so it can take different values and so on. So it doesn't have a fixed value. So such variables are that are called as symbolic variables. So what we'll do is we'll uh, try to see how symbolic variables can be defined in MATLAB and how we are able to solve some equations related to this. So anyone who is very new to MATLAB and seeing the screen for the very first time, haven't used it prior to this. Okay, one, there are some here. Okay. So I'll just quickly tell you what exactly this is. So when you open MATLAB, your window will somewhat look like this. On the top corner, top ribbon, you will have different options of home, plots, apps, live editor, etc. So there are different options. We'll see what these options do. In the left hand side, there is the folder that you are actually into and all the files that are there in this particular folder. Uh, Here in the center part actually is the part where whichever file you're opening, we are able to see that here. And in the lower bottom, this is called the command window. So basically with the command window, we can actually write any code and execute it. But it's like, for example, if I write a equal to 6 and just hit enter, you can see that I'm able to execute that particular command and the value of a has been assigned as 6. So you can actually write your entire code in the command line itself. The only restriction or only limitation over here is that you won't be able to, if you want to rerun it, you will have to write the entire code again. And to avoid doing that, what we do is we'll try to save that script as a file so that whenever you open that file, you have all your lines of codes ready. If you want to make some changes, you can do that. And then you can just hit on run and those set of commands will be running. So you don't have to write those lines of code every now and then. That is the difference between using a command line directly and having an editor. Okay. And whatever variables you are declaring, whatever variables have been saved, all those variables you can see in the workspace area. So this is the space where it will, the next time you are accessing that particular variable, it will be accessed from this space. So right now when I wrote a equal to 6, you can see that it has got saved over here. That is the task of the workspace.
Is the text visible or do we need to make it larger? A bit larger.
This is okay? Slightly more.
Yeah, they have it on the screens.
Yeah. So again, this particular script is what we call as a live script in MATLAB. So for people who are very new to MATLAB or using it for the first time, there are two types of scripts. Again, there is one which is called as live script that is open on the screen right now. And there is something called as the normal MATLAB script. So if I go here, there is a button of new. If I click on that and click on script, this is the traditional MATLAB script that opens up. So you can have your code written over here. It will work exactly the same way, even if you write it in live script as well. The only difference over here is here you can just write piece of your code. And if there are any comments or anything extra that you want to add, that will be just added as comments as percentage symbol. So I can write here as this. Something like that. Okay. So this is the only way to add comments or any other information that you want to have in your piece of code for better understanding of that particular code. Whereas if you look at the live script, you can do a lot of more things here. As you can see that there is a text of entire theory that we are trying to explain over here. There are some images over here. There are some equations that we can put. And then there is some part of code. So the gray area that you can see is the code part that actually will be running when you run that particular code. All other things are just for your understanding and your reference. Just like how we write comments in the normal script. This also is somewhat like comments. It's not going to run or anything. I hope that's clear, the difference between what MATLAB scripts and live scripts are. So in this part, basically clearing the workspace, that is clear all. This is a command that will clear everything. And CLC is just for clear, that will clear the command line. So if anything has been written prior to this in the command line, that will get cleared. And with clear all the workspace and all the figures and everything, that those things will be cleared off. And on the left hand side, if you hover over that particular section, you can see that there is a blue ribbon that comes in. When you click on that, it will just run that particular section and not the entire code. So there is a button of run over here. If you click on that, the entire code from the line 1 to the last line will be executed at once. If you click on this particular ribbon, only that section is running, and the execution will halt after that. Okay. So the next part is, I'll just clear all the outputs. Okay. So the next part over here is what we are trying to do is we are trying to declare some variables. So in the first line here, you can see that pi by 6 and pi by 4 is written. So basically, pi is a variable, as we all know what exactly pi is. So it's the value is something closer to 3.14. But when we are writing just pi as words over here or as a word, MATLAB knows what exactly it is. So it is an inbuilt function kind of it. It is an inbuilt function. Okay. So when I run this particular section, you will be able to see the differences between the three lines. It's the same line, same piece of line that we are running, but in a different fashion. First one is just plain. So plain pi by 6 plus pi by 4, and it is giving me the value of the addition of these two. And it's giving us 1.3094. So it's just a number that I'm getting. In the second part, I'm writing it as a symbolic. So sim stands for symbolic variable. So I'm telling it to MATLAB that my pi by 6 variable should be a symbolic variable. Okay. Similarly for pi by 4. So what you can see is it's not actually simplifying the decimal part and putting it as 1.3094, but it is writing it as 5 pi by 12. This is what we actually expect when we are solving some computations in mathematical computers. We don't want it to simplify because it's pi. We want to keep it as pi only. So this is how you can actually change those things depending on your requirements. Again, you can specify it as a variable precision arithmetic variable. In that situation, basically a variable precision arithmetic is that it will have about 32 digits into it. So you can see that there are 31 decimal points and one is the ones place over here. So now depending on how much digits or how much decimal places you want to have, you can. So that is the difference between the first part and the second part. You actually wanted more precision into it, more decimal places, so you use this one. Okay. So this is a very basic example where symbolic variables came into the picture. So what we'll do now is what we'll try to understand is a basic projectile motion. So everyone might have sometime like studied what exactly a projectile motion is, right? It's just any mass that is being thrown in air or in vacuum or anywhere, and the motion that it follows is the projectile motion. Yeah. So what we'll do is we'll try to come up with the parameters, or we'll try to solve what exactly is the range of it, what exactly is the maximum height of it when it is projected at a velocity, and at an initial velocity, and how the trajectory will look like. So to do that, what we do is we have some initial parameters, like what should be the starting velocity of it, what is the mass of it, constant of gravitational constant, etc., and the angle, and so on, because these are the parameters that are the initial starting point of any projectile. Okay. This is a very simplistic problem. We are assuming that these things are happening in vacuum. So there is no drag that is being put onto that particular projectile. There is no change of density because there is no air, there is no density of air. So it's just a projectile that is being fired, nothing else. So we know that from our experience and from what we have learned that it will follow a it will follow a parabolic, inverted parabolic kind of trajectory, right? So now, given this information, maybe in ninth or tenth standard we have tried to we have derived what exactly is the formula for maximum range, what is the formula for the height that it achieves, what is the entire time duration that the projectile is in air, and all those things. Okay, so if we were to do the same things in MATLAB as well? So these are the same equations of motion. These are the basic fundamental principle equation that we start off with. And then we try to put in our projectile conditions into these particular equations of motion. Okay. Because and then we split the entire motion in two directions, that is in x direction and in y direction. In x direction, there is no acceleration, so the velocity will remain constant. And in y direction, there is an acceleration in the opposite direction due to gravity. So that becomes a motion with acceleration, and the x direction motion is without acceleration. So again, these are simple equations that everyone might be aware of on how these are coming. So x will be u cos theta t, and similarly y will be u sin theta t minus half gt square.
I think you can zoom in a bit. Does everyone understand projectile motion? Is there anyone who's not seen this stuff before?
So what we are trying to do now is we try to model these equations in MATLAB. So the first and foremost step is here when we start declared pi by 6 as a symbolic variable, we wrote the keyword sim and then put pi by 6 into the bracket. So MATLAB knew that whatever is written in that particular bracket is a symbolic variable. Similarly, what we do here is we first declare our symbolic variables, we define those. So sims over here is the keyword for that, and we declare t, x, and y as my symbolic variables. So that is the first step that we do. And then we just write the equations the way we write. It's just u into cos of angle into time. Similarly, y we write it as u sin theta minus half gt square. Okay. And then we are trying to plot this. So I'll just run this particular piece of code. Sorry, I didn't run this particular section. So that's why it's showing me error. So you can see that when I'm writing this particular equation, it's giving me x equal to a constant into time. One more thing to note over here is it's giving me the entire equation. It's not trying to solve what exactly root 3 is. It's not putting that value as 1.73 and then giving me the value. That is the difference between normally how we are computing some variables and what happens when we are declaring a variable as symbolic math. Okay. In the next equation also, it's writing as 50t minus something t square. And that something is a fractional part. It's not trying to solve that further. It's not that it can't solve it, but it's just keeping it as it is because we might need it for our computations in that way. Okay. And then, as I said, we try to plot this thing. So we are just trying to plot this from 0 to 10, roughly 10.2. And then these lines are just to label that particular graph, right? What the x-axis is, y-axis is, and the title is. And this graph it looks somewhat like this. So this is x versus t. Because there is no acceleration, it's a constant velocity motion. It comes as a straight line. Everyone is able to understand up to this part what we are trying to do. Yeah. Okay. So basically what semicolon does is So what semicolon does is, as I have put semicolon in these lines, the output of that is not shown over here. That's the only thing. The output is being suppressed. It's not that it is not computed. It's computed, it's saved in the workspace. It's just not printed on the screen. Okay. That's the only difference with having a colon or not having a colon. So wherever I am not having that particular colon, so here I'm not having it because I wanted the equation to be displayed on the screen. Okay. Yeah. Yeah, I'll just come to that.
Line on the decimal part, if I want the equation decimal.
Yeah.
So how can we change it?
You can do that. I'm coming to that part sometime. Yeah. So you are asking about fplot, right? Okay. So this fplot is an inbuilt function in MATLAB, and there are a lot of inbuilt functions in MATLAB. So if anyone who is not aware of, if he sees come across a function for a very first time, you can just either go in the command line, write doc fplot. It will open a documentation for that particular function with all the syntaxes, all possible syntaxes for that function. So this basically says that plot expression or function, and then there are different syntaxes of this, and if you click on a particular syntax, it will actually show what it is doing. Plots over a specified interval between, and if you have that array of x min and xy, it's plotting in between that. That's the thing. And if you need some examples, you want to understand it through an example, you can click on examples. There will be some examples also for that particular syntax. So that will help you understand in a much better way. And this is for all the inbuilt functions that are available in MATLAB. If you are not understanding it, what it does at the back end, you can open the documentation page for it and read it through and understand. Okay.
Just checking, like, is everyone able to follow the syntax and what's happening here? Okay. Is the symbolic method different to what you have seen before in computing? Okay. So there is a reason why we're showing you this stuff. All of these commands are part of the symbolic math toolbox. So if you have an analytical solution to whatever problem you're working on, what we're trying to show is you can directly put in the equations into MATLAB and come up with a solution or a plot without having to write any kind of mesh or any kind of solver. Okay, you can directly put in the mathematical equation and generate the plots from that. However, there are times when analytical solutions are not available or they don't work. In that case, we would then have to go to the numerical computing part, which is the main part of what we're doing. Just checking, is our speed okay or it's too slow or what's going on? Is it okay? Okay. Just tell us if you want us to go faster or anything because we're not able to judge it from here. All right.
Also, Dhruv just mentioned on analytical solutions and numerical solutions. I hope everyone is aware of what exactly analytical solutions are and numerical solutions are. If anyone is not aware, please let us.
They'll see. Yeah, next thing.
So this was the plot between of x versus time. Similarly, we do the same thing for y as well. Now, because it's a accelerated motion, a negative accelerated motion, it comes as an inverted parabola. So these are just, we are trying to plot x and y with respect to time respectively. Now, as I said, we will try to find the entire time of flight and other parameters that we have. So entire time of flight is the time which the projectile was fired to the point it reaches the ground. So what was the time taken by it to reach the ground again? So to do that, what we do is we just put y equal to 0. So wherever it will hit the ground, which is y equal to 0, we'll try to solve that. So here also we again define another variable, symbolic variable as t. And what we are doing over here is I'm equating it to solve. So solve is again an inbuilt function in MATLAB, which will solve this equation. So I'm putting y equal to 0 and I'm solving it for t. So this is the meaning of this. Again, you can get into the documentation of solve on why this syntax is there, but this means that why we are equating it to 0 and we want it to solve for t. Whatever the answer is coming, I want it to be saved into the variable capital T. Okay, so I'll just run this section. So you can see that for this particular line it has given me two values. Okay, so now it's giving me two values because at time t equal to 0 also it is at y equal to 0, and at sometime when it hits back, it will be again y equal to 0. That's why there are two equations. So now obviously the second one is the answer that I'm looking for. So now someone asked me from here, if we want to convert it to a decimal point, what we can do. We can, again, there are different functions that we can use. Double is one of them. So it's the data type which you want to convert. Depending on your requirement, you use that particular data type and try to convert it. So now when I'm using this particular function, it is giving me 0 and 10.19. So it actually converted it to a decimal point. Now again, I'm having these two values in the variable capital T. What if, and the first one is definitely not the one which I'm looking, but it's still being saved into it. It's not a mathematical issue. It's just it's trying to solve what we have asked it, but we are not requiring that. So what we do is we try to remove that particular value from the variable, from that particular array. Now, and this is what we are doing is that as indexing. So what I'm doing is I'm writing a variable idx equal to t greater than 0. So wherever t is greater than 0, wherever this condition is satisfied, that particular value will become 1. All other values will be 0. So it will be a 2 cross 1 logical array again, where only zeros and ones are there. So wherever t is greater than 0, you can see that it has become 1. Other is being other value is 0. And when I pass this index array to t, then I'll just get the value which is capital. So basically, wherever it is 0, that value is omitted. Wherever the value is 1, that value will be saved into the other variable that I'm calling. I hope this part is clear what we have done. Okay. So now we can see that I just have one value, that is 10.19, which is what I was expecting. That is the total time of flight. Similarly, we do similar steps for calculating the range. That is the distance traveled by the entire projectile in x direction. And to do that, we just substitute. So we now know what was the entire time of travel. So at t equal to capital T, what is the value of x that has traveled? We just substitute that. So in the equation of x, which is of the variable t, instead of t, just substitute the value as t positive, t underscore positive, which is 10.19 something. So this function is just helping us substitute that particular value in our symbolic equation. And this again, the next line, I'm using it to convert it to a double. You can see that the first answer that I got is again in a symbolic way, symbolic representation, and the second one is in a decimal format.
Yeah, I think people get it like, okay. Yeah.
Similarly, for the maximum height, we do same thing, substitution of the half of it, because at the peak, the time is half of the total time travel. So that's what we are doing over here. Or we try to do it using the maxima method. You differentiate it. Again, DIFF is a function which will differentiate your function, and you equate it to 0. It's the same answer that you are going to get in both ways. And then here in the last part, we are just trying to plot x versus y. This is the expected behavior that we saw for a projectile motion.
I think we need to make this a bit more practical, otherwise people. Okay. So are all of you able to run this script? And all of you kind of get it, right? Okay. Now the thing here is we have seen this projectile motion problem. Do you think we could use this in real life for designing an airplane or any other thing that you're kind of throwing over a long distance? No, why not? Okay, air resistance is there. What does air resistance do? It takes away some energy, but what does it actually do in mathematical terms?
The one more extra term will be
So what we've done in this case is we use the equations that Mr. Newton derived and we plug them in and we've got the solution. Okay. However, that ideal solution does not work in the real case because there is air resistance. So what you have to do is model the effect of that air resistance, because a real projectile will not behave this way. As it flies, it will lose energy, which means it will not achieve that maximum height or that maximum range. Okay. Now, if you include air resistance in this problem, it becomes actually quite hard to get the analytical solutions. You can do it because it's a simple problem, but sometimes it's just easier to come up with a numerical solution. Okay. Can anyone tell me how a numerical solution for this problem would work? Okay, I'm Euler or Newton or whatever it is. How do numerical solutions actually work, like step by step? Right. So what you do is you take this entire problem, this entire trajectory, you split it up into small pieces, right? And you assume that the problem is, let's say, kind of linear for that small piece, or you can compute the solution. And at every time step, you recompute the values of acceleration. Okay. So what will happen is right now, gravity is applying a constant acceleration downwards. That will continue to apply. What else will happen as the projectile is traveling through the air? Okay, so whatever direction the velocity is moving in, the drag force will apply in the opposite direction. Yes. And drag, just empirically, we know that drag is proportional to the square of velocity. Empirically, we know that from measurements. So the faster your body is moving, the more will be the drag force slowing it down. Right? So your drag force will be much higher in the earlier part of the simulation and much less later on. So basically the forces on this body will be changing throughout the whole simulation. That's why you cannot assume a constant force. You have to compute at every step what the force is, depending on the current value of velocity, and then figure out what the correct solution should be. Does that make sense? Yeah, okay. Right. Shall we go straight to it, or do you want like a 5-minute break for 5-10 minute break? Okay, we can go straight to it.
So what we are doing now is we are trying to model the same set of projectile motion, but as Dhruv mentioned, we are taking it to a real life example where there will be some kind of a drag force. Now it's not in vacuum, so there will be drag forces, or if the height of the motion is way too high, we'll also have to consider the change of density, air density, because due to change of air density, the drag coefficient will also be changing. So this becomes very tedious or difficult to solve in by an analytical solution, and that's why what we do is we try to solve it piecewise for every instance of time for small, we try to increment the time steps and try to solve or try to find the y value of it and then come up with the entire equation. Okay, so these are some of the equations. Maybe you can have a look at it later as well. But as Dhruv mentioned, the drag force is being implemented over here, which is proportional to the square of velocity and acts in the opposite direction of the velocity. So the direction of drag force is also changing with every increase of time, uh, and its magnitude is also changing. So this becomes
On the latex.
yeah. So I'll just open this. So if you want to add any LaTeX equation into these particular live scripts, so you go into this particular insert option that you can see here, and then there is an option for equation. You click on that. You can directly add equation, but or you can use the LaTeX way of doing it. So if I click on LaTeX, this is how it looks. So if I were to write something y equal to yeah x sine. So in LaTeX, if I were to write theta, we have to write it like this. And the preview of it looks is shown. So how whatever you are writing, how it will be looking, you can see here itself, and you can make necessary corrections. So how the way you write it in LaTeX, the same code kind of thing that you have to copy and or write it over here, and you can get the equivalent equation in LiveScript directly.
Let's mention the export to PDF.
Yeah. Also in Live Editor, this entire script can be exported as a PDF. So again, there is a option over here of export. You click on that and you have different options. If you want to directly convert it to PDF, you can use this. Or if you want to convert it to LaTeX and then put it into your LaTeX journal or something, there is a way to do that as well. Okay.
Yeah, the pain that we're kind of trying to address here is earlier when we used to work with scripts, when you want to copy and paste the code, let's say in a paper or even in your thesis, you typically had to import it into Word and then all the formatting gets messed up, right? So what you can do now is you can just go to export and then export directly to PDF, and that entire thing, maybe just save it in the same folder. That entire thing will then be, properly formatted and come out looking like that. So it's a PDF document. People are even writing books using this stuff now. Or the code itself, you can just select and export that to LaTeX, and that you can import directly into the papers you're writing or into your thesis. So everything will be properly formatted and it should come out nicely.
So again, for the same part, we try to declare some initial variables the way we did it in the previous step. So now we'll have to also include the coefficient of drag for the projectile and the area of the projectile, because now we are taking a real scenario over here. So I'll just run through that part and go ahead. Here we are also setting the angle of it. So what is the angle of firing for that particular projectile? You can see that there is a slider kind of a thing here. Again, you can go into controls. You can select here. If there is a variable a equal to something and I want to add a control to it, you can act. There are different controls over here. There is a numerical slider that I have used. You can use a checkbox button, etc. So you can explore these options as well, depending on your requirement. And what we are trying to do over here is the first step is again we are converting the angle that we took in degrees to radians for calculations. The second line over here, what we are doing is we are trying to create an array, one-dimensional array with all the initial parameters into it. So that when we are using some functions in the next part of the code, we can just parse this particular array into that particular function. So it's the same data that we took initially, we are just putting it into one variable, one array. Okay. And then we are declaring some time step here. We are declaring it as 0.01. So that will be the time step for my solver on how after how much times each value should be computed. Okay. So now what we are trying to do is we have the initial parameters being set. We try to solve this particular problem numerically using the first order method itself. So by first order method is we'll just try to calculate the slope of the graph, and depending on the change of the slope of it, we try to manipulate or we try to calculate the value of y. So it's like there is a function, and we for that particular point we know the at what rate it is changing. With that we calculate the next step. Then again we compute the change of that the rate of that particular equation, and again and so on. That process is being followed throughout. That is how we are going to solve. And to solve that, what we do is we create state variables. Now, state variables is an array of the states at time t equal to that particular instance. And that is what we are trying to compute for every time step. So if you can see that what we are doing is we are declaring a state variable z with these parameters into it. Now, y of t is the vertical distance from ground at time t. Similarly, Vy is the velocity in y direction at that time. X is the position in x direction for the projectile. And similarly, Vx of t is velocity in x direction for that projectile at that point. So, and then we differentiate that particular state variable and name it as dz. And again, when we write differentiation of that particular thing, we can replace it. So y dash of t will be Vy of t, because differentiation of displacement is velocity. So this will be Vy and this will be Vx, and these two terms come up as acceleration, because differentiation of velocity is acceleration. Okay. Everyone is able to understand what z and dz is, because if you understand this, majority of the part of the solver becomes easy.
Yeah, I just want to quiz people on this part because typically this is where people start getting lost. Okay. Does anyone have a small object we can throw around? Like a ball? Do a practical exercise.
Yes.
You understand the dot notation? Yeah. Right. You see, okay. So when we start taking, people don't actually get it. We'll try to explain this through a practical demonstration. Does anyone have a small object I can throw? Okay. You have a tomato. Tomatoes are expensive, man. Okay. Can I have a friend here who's good at like catching things? Okay, come. Okay. So this is my projectile, right? This orange, red kind of thing. You can come in front of the camera if you want. Okay. You can stand there. So I am the origin point. He is going to catch it. So I'm going to throw this thing at some angle. Just watch for it with some velocity, right? So there it goes, and he's got it. Okay, good hand-eye coordination. Mine is not so good. So as the projectile was flying through the air, what are the things that are changing? Velocity, x coordinate, y coordinate. Okay, let's break this down. So we have created a state vector called z. Okay, what does a state mean? Okay, a state is some condition that your system is in, right? So what are the states that we are measuring for that object? Position and velocity, okay? But it is in 2 dimensions, okay? So the first thing that we are measuring is the y displacement. Okay, what is the graph of y displacement going to look like? Parabolic, right? It will go up, then it will go down. Yes. What is the second state variable? Velocity in the y direction. Where does it start? The graph. Everything starts at t equals 0. So what is the initial velocity? Whatever I throw it at, right? So velocity times the sine of theta. The sine of
Yeah, sine.
V sine theta. Okay. So we start at V sine theta. Then the projectile is rising but slowing down, and then it reverses, and then it comes back down on the other side. So what does the graph look like? It's a straight line that starts at V sine theta, hits 0 right at the top, and then it drops down and gets you minus V sine theta at the other end, approximately speaking. Okay, so you can imagine Vy in your head.
Yeah.
Same thing for x coordinate. What is the x coordinate? No, it's not. X is not V cos theta.
X is rigid.
What is the x coordinate? Just throw it back. I try to catch it. Got it. Right. So I am throwing this ball from here. You understand which direction is y at this point? Up. Okay. This is the positive y direction. What direction is x? X is that. Okay. So I toss this thing. The y changed. Did the x change also?
Yes, sir.
Okay. How did the x change?
V cos theta into t.
X change linearly, that's what we were looking for. Okay, there is no acceleration acting in the x direction. Like it is not like a rocket ship where you fire it and there's thrusters coming out the back and speeding up as it's going. Whatever velocity I gave it here, that is what it will travel with, not counting air resistance. So x coordinate is this distance, how far it is, and Vx is the velocity it is moving with. Now do you understand the state vector? So if you know the state vector at any time step, you should have perfect knowledge of what that system is doing. It captures all of the information necessary, but no more. Make sense? Is there any information I'm missing? Yes. What is the dash mean? Okay, good. Okay. So can you just make an array in MATLAB? Go to the command window. So I think we made a small mistake, like we should have shown you the MATLAB syntax first. Just make the command window full screen and make the text bigger. Okay. So just make an array in MATLAB 1 to 10. Okay. So if you define an array as a vector, which is like this is like a row vector. You can see all the elements from 1 to 10 are in one dimension, right? So MATLAB stands for Matrix Laboratory. It's used in mathematics because you can directly put in things that are useful for matrix computations. How they are useful, you'll see throughout the workshop. Now, if you just type array apostrophe, just see what happens. Okay, the whole thing turns into a column vector. So it's basically a transpose. Okay, so the reason we are taking a transpose of that, we can go back to the equation. Yes, so just maximize that equation now. So the state vector that we have is y, vy, x, and vx, and we are taking a transpose just so we are consistent whether it's a column by solution or a row by solution. That's it. Okay. So everyone understands the state of the system that we are in. Yes, we explained practically enough. Important. Now, if I take dz, which is the differentiation of the state at every time step, we get that expression there. So let's try to kind of understand. Can I have that, please? Thanks. Okay. So suppose I have launched this projectile and it is somewhere in the air over here. It's moving this way. Okay, so it's going like that. Okay. What is the differentiation of y here? Which velocity? You have to be more specific. dy. Okay. So my state vector y is this direction. So when I differentiate that, that becomes what? Vertical velocity. Okay. So the first element of that dz is telling you how fast this thing is moving upwards. Upwards or downwards. If it is up, it's positive sign. If it's down, it's negative sign. Okay. What's the second one? What was that?
What's the rate of change of vertical velocity?
What is the rate of change of vertical velocity? Okay. What is the rate of change of vertical velocity? Can anyone answer? Minus g, right? Why? Okay. So as this thing is traveling upwards, it is being pulled that way by gravity, always acting down. Okay. So v dot y of t will always have a negative g acceleration acting downwards. So the value of that will all, I mean, it will be negative g, but we'll add a little bit of air resistance component to it in a short while. Everyone got that? Okay. What is x dot t? Rate of change of x that way. What is that? That's the velocity, right? Okay. So the interesting thing, what you note is that y dot t, which is dz, index number 1, is actually the same value as z of 2. Yes. So when you are solving these differential equations, dz1 is the same as z2. So you can just copy the value from there. Okay. And the second element, Vy, that you have to calculate at every time step. Similarly, xt, you just copy from z. And the acceleration value you have to compute at every time step. Okay, so what is v dot x in this direction? It is 0, but air resistance will slow it down ultimately. Okay, so it will be, there will be some negative air resistance acting that way. All right. So all of you, do you understand the state vectors now? Do you understand what the state vectors are? See, the reason is we are showing you this method is projectile motion is very easy. Most of you can do it in your sleep. However, whatever equations you're trying to solve, it will be built on exactly the same structure because all the ODE solvers in the software packages, they use this structure. You have to define the state and then you have to define the gradient of the state and then you have to calculate that. Okay. Thanks. We'll use this format. So thanks. Yeah, the round of applause here, please. I'll just hold on to your tomato substitute here. Okay. Yeah, let's go through a little bit of the code, then we'll do some more explaining.
So what we'll try to do is in our script is definitely we saw that how we declared the initial parameters. So this is the main script that we are working on. So in this particular main script, we have the parameters, we have the solver selection part. So we'll select what type of solver it is. Here for this particular part, we are doing it through the first order solver. And then once you get into which exactly the solver is, you get into the which one to use. So first order solvers is the Euler's method, and the fourth order is Runge-Kutta. So we will be using these two, and then we'll see how variable step solvers also work on. But for now, just focus on understanding this, that the main script has the parameters and solver selection part. Then we get into the ODE solver, which solver that we want to use. And then depending on which solver we are using, we try to compute dz accordingly. And one more thing that I would like to add is we have the state vector, we have the derivative of it that we are computing is dz. Why we are going into derivative is because the entire problem is what is we are trying to break it into small pieces to make it piecewise linear. Okay. And when we are making it piecewise linear, to predict the next step of a linear equation, if you have the point of a line and the acceleration of it, you can actually predict the next line. Right? You have the entire equation of the line with just two parameters. So we know the current state variable, we know the dz of it, we predict the next part, go over here, then predict the dz of it, go to the next part and so on. That's how we are coming up with all the points of that particular equation. That is why the dz part has come over here. Okay. So in the code part, just we are using as I said that we are using Euler's method over here for this particular example. So to do that, we are just selecting solver as 1. That is how it has been programmed. And then we call a function called as ODE solver. So I'll just open that function.
I'm not sure they know how to work with functions. Write our own option. We can define that. Sorry, just checking. Do all of you understand how MATLAB functions work? Inputs, outputs, and all that? Okay, who here does not know how a function works? Just raise your hand honestly, because we will show you them. Okay, few people are new. Who else? There. Okay. So how about we write a simple function and show you how this thing works step by step? Would that be okay? All right. Shall I do that? Unless you are comfortable. Okay. Okay, so we are going to go back to the basics. I'll just write stuff in the command window. You can follow hands-on or you can just see what's going on. So we are going to diverge away from the script a little bit and just understand how functions work. All right, I'm going to clear everything in my workspace and just start from scratch. And the screen is still visible, right? To all of you. Okay. Make the font a bit bigger. Okay, so let's say, first of all, how are functions called? Let's say I create a simple time vector going from, let's just call it t, it goes from 0 to 10, like that. So if I type that, that creates an array of 11 numbers going from 0 to 10. Okay, straightforward enough. So if I just write t equals 0 to 10, it creates an array 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Now suppose that I want to call a function on these numbers, which are going from 0 to 10. What I can do is either I can run a computation directly on that variable, or I can call a function. So let's look at both of them. So suppose I said t, let's say times 2, like that, and I hit enter. What you will see is that every single element of t has doubled. Make sense? Yeah. So we can call mathematical operations directly, or we can pass those entire set of values to a function. So let's say I use a sine function, sin t, and that will compute the value of the sine of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. So basically the syntax of a function is you have a keyword, which is the name of the function. You pass it some input arguments and it gives you some outputs. Okay, so how do we define a function in MATLAB? What you can do is you can go to the top left-hand corner and then new and then function. Okay, so when you click on new function, a blank window will open up, and this is how you write functions inside MATLAB, and we'll also show you how to call them. So you will see this weird looking syntax. We'll just explain what this means. Just click on new function. Okay. So the way a MATLAB function works is you use the keyword function and then you write what your output arguments are. Then you say equal to, and then you put the name of the function here. So let's say I want to create a function that gives me the square, it gives me the square, the addition of the square of two numbers that I put in, let's say, and maybe also the mean. So I'll say, I'll call this custom function. I'll give it that name. And I will say, give it two numbers, A and B, like that. Okay. And what I want is sum of squares as the output. And I want the mean as the output. Now I can write a summary of the function. So this function takes two inputs and returns sum of the squares and mean of the numbers. All right, and this is where you write your code. So the way that functions work is you pass in two input arguments after the function name. You do your computation in this kind of blank space here. And these numbers, which are the output arguments, these should be computed here and they will be returned. So how would I calculate the sum of squares? Can anyone shout out the syntax? A square plus B square. Okay, so you are saying A star A plus B star B, like that, right? Okay. Let me show you again one thing that trips up people about matrices. So remember, every single thing that you do in MATLAB is a matrix, each of these numbers. Okay. So if you remember, I had this variable t whose value went from 0 to 10. So if I multiply t cross t, first of all, it will throw an error. It will say incorrect dimensions for matrix multiplication. Why is that? Okay, because T is a 1 cross 11 matrix. So if you want to multiply a matrix that's m cross n and the other one has to be n cross p, right? So those interior ones have to be constant. So either you can multiply a square matrix or what you can do is element-wise operations. So the way element-wise operations work is you have to write T dot, and this is the power function. This is shift 6 on my keyboard, which is this little hat sign. And then you write the power, let's say square. So what this will do is that will apply that mathematical operation element wise in a matrix. So if I do t dot square, I get the expected result. Okay. So 1 square is 1, 2 square is 4, 3 square is 9. It is making sense. Okay, so don't get confused if you see dot some mathematical operation. That just means element wise. So if I have to compute the sum of squares and the mean, what I can say is a dot square like that plus b dot square like that. So hopefully this will be a little bit more robust. And I'll suppress the output because I don't want to see all the garbage on my screen. How do I take the mean? A plus b by 2. Okay. So let's just keep it simple. You can say a plus b by 2. And that will give you the mean. But this is not correct because what's going to happen here? No bracket, right? So you have to do that. All right. Once you've written your own function, what you need to do is just save it. And the name you save it by always has to match the name of the function. So this is why you cannot create your custom functions which have the same name as a built-in function, because that might create some conflict. So custom function is okay. So I've saved it.
It should also be in the same directory where you are working in.
Yeah.
Or the same folder where your files are.
Okay, now how to get the outputs? So if I say custom function, let me put two numbers, let's say 2,3. It is giving me only one answer right now. What does this answer look like? What's 2 square and 3 square? And then add them, you get 13, right? So I created a function which should have two outputs. It's only giving me one output. So this is what happens if you if you call a function without specifying the outputs, it will only return the first output to you. So you always have to make sure you understand what the function outputs are and then demand them in the format that you need. Okay. So the way you do it is you call it in square brackets. Square brackets is how you create a matrix. So let's say I call SS and I call M equals custom function 2,3. Okay, so my input is 2,3 and my output should go to those two variables. When I call this, hopefully I get the right result. Does that look right? Okay. Is everyone now clear on how functions work? Any doubts? Are you all able to write this stuff like as we're doing it? All right. Yeah, maybe we just walk them through OD solver and then have a break kind of.
So as we can see that in this particular function named ODE solver, we are taking 3 input arguments and it's giving out 2 output arguments. That's how it is being designed. And in this particular first part of it, we are just setting the initial conditions of it. So we are starting at t equal to 0. That's why the first element in the time array is being put as 0, and as it increments we'll be putting in the values of t in that particular array. So time array is it will start at t equal to 0, it will increment by some time, it will be that value will be put over there, then again it will increment, that value will be put as a third element and so on. That is how the entire time array will be created. So as we were saying that we are looking at z as the state variable and dz as the derivative of it. So we are declaring the first elements of z. So z of first was the vertical displacement, right? So and the first element of that particular variable is the position y position of the projectile at time t equal to 0 or the starting point. So that we are putting it as 0. Similarly, z2 of 1 was the velocity in y direction. So the first value of that we are putting in as r1 of sine r of 6. So now if you go to what r is, it was the parameter variable that we created and that we are giving it to the function, and it looks like this. So what exactly is r1? R1 is the v naught, that is the initial velocity, and sine r of 6 is basically R6 was basically the angle of it. So we are computing sine of it. So it is basically u sine theta that we are putting it as velocity in y direction. Similarly, we do that with the horizontal state as well. X0 is 0 and u of x is r cos theta. Okay. Then because we will be doing this for different time steps, or we want to reiterate these steps. So we initialize IS1, and this is something that is coming for the coefficient of drag. Okay, so R4 again is, if you look over here, is Cm. So we are computing Cm into Am by 2m. Cm is the coefficient related term. A is the area of the projectile and m is the mass of it. So that is what we are computing over here. That will help us to calculate the coefficient at that particular height. Okay, and then with this is we loop this into, and as I said, for a particular height we are computing the density of it. Again, density is a user defined function. I'm not getting into that, but what it does is it calculates the density of air at that particular height. That's it. Okay, and that is being multiplied with the drag coefficient to get the final coefficient which is giving the drag for us. And then we increment I, and then we compute the next value of t. So next value of t, or the current value of t over here, would be the previous one plus the time step. Because this is first order solver, the time step is going to be fixed. And it is a fixed solver, that's why the time step is going to be fixed. We are not going to change the time step, the change of time steps over here. And here is how we are actually selecting the solver. So as I said in the first script, that solver is equal to 1. So we are just using the Euler's method over here. I hope these steps are clear. Anyone having any queries on the flow of commands over here? T as in T increment is a value that is coming as an input variable. It's an input argument that we are giving it as when we are calling the function. And once we have these things set, we then calculate which of the solvers we are selecting. That here we are going to get into the Euler's one. So then I open this particular function. So this is just calculating the dz value of it. So this is again a user defined function that is being written. Dz is a function which computes dz for us. And once we get that dz, we will try to calculate the next state variable. So dz is basically the derivative vector, and we are just multiplying it with TINC. So if you look at this particular formula, this is what the Euler's method says. So Euler's method is current value will be equal to previous value plus time step into the change rate of change. And if we get into this particular function, it's the same equations of motion that is being coming over here. We are just saying dz of 2. So that is the acceleration is proportional. K2 square is the velocity. K2 is the velocity. Sorry, Z2 is the velocity. We are squaring it up and multiplying it with K and subtracting it with G, because the acceleration is proportional to velocity in y direction and there is a factor of G. So that is why it is written in such a way. And depending on whether it's going up or going down, the direction of that changes. So Z2 of, we are checking the condition whether it's going up or it's down. So if it is in positive direction, it's going actually up. If it is in negative direction, it's going down. Similar things we do it for the X direction as well. Here you will see that there is no effect of gravity because it's in X direction. But again, the velocity is proportional to the drag is proportional to the square of velocity, and that's why this factor is coming in. So this is the actual equations for the projectile motion coming in this particular solver. Now, depending on your application, things might change over here.
We go back to that flow chart we had.
Yeah.
Still. That
Not this one.
no, it's there only, just above. Just zoom in. Okay. Is anyone confused why we wrote it in such a complex way? Are you able to follow first of all? So we would really like to make sure that you understand that function dz, because if you understand that function, the rest of numerical computing is very, very easy. That is the only tricky step. How many people honestly right now understand that function dz? Just show me your hands. Less than half. Okay, so let's spend some time here. Because this we definitely want to understand. All of you understood what was the state vector, right? What was it called? Z, right? Where is that thing marked here? Okay. The way that ODE solvers work is that suppose I'm throwing this projectile that way. Okay. So I start at a time step of 0 and I break it down into two dimensions, x dimension and y dimension. Okay. If anyone can't see you, you're welcome to get up and come and see. Because this is quite important. I hope everyone can see. All right. Now at this time step, this projectile is moving this way. One component of motion is in y direction, one component is in x direction. Okay. Now what the solver is actually doing is it is seeing this direction of motion and then moving the time step forward by 0.1 seconds. Okay, so actually you're stepping forward in time in increments of 0.1 seconds. So first it is here, then it is here, then it is here, then it is here. And at every time step, it is computing where it is going to go in the next 0.1 seconds. Make sense? Okay, because the equation is actually changing at every step because the forces are changing at every step. So you have to break down the problem into this discrete time steps. Already. Now suppose this projectile is over here. It has a vertical velocity and a horizontal velocity. First, let us think only about horizontal velocity. So this projectile is moving this way. What is the force acting on it? Is there any gravity acting on the x direction? No, right? What is the force acting on it? Minus kv square. So k is some air resistance coefficient that we calculated. Multiply that by the square of velocity. If my projectile is moving this way, what direction is the force? Opposite direction, that way. Is that clear? Okay. So now can we go back to that dz function? Okay. So what we are doing in that dz function is solving all of these things manually. So if you remember, z4 was the horizontal velocity in our state vector. So if z4 is greater than 0, then dz4, the rate of change, is minus k times z4 squared. What does that mean? Are people getting confused in the syntax? Okay.
Horizontal velocity is bigger than 0, then it will have this subtract opposite direction.
Yeah, the force will be the opposite direction. Okay, so z4 is horizontal velocity. So if my body is moving in positive direction, the force will act in negative. Similarly, if it happens to be the velocity happens to be less than 0, then the force will act in a positive direction because it is just opposite. Okay, so that piece of code which looks kind of ugly that's all it's saying. That you square the velocity, you multiply it by some coefficient and apply it in the opposite direction to where it is moving. Is that clear? Some of you are looking very kind of hazy, but I hope this is making sense. All right. X direction is clear, I hope. Now let's talk about y direction. So my projectile is moving in y direction, that is upwards or downwards. Okay. So z2 is what? It's my velocity in y direction. So if my velocity is positive, which means this thing is moving upwards, what is the drag force? It's acting downwards, that's why you see minus kz2 square. Okay, so that's all that means. If this body is moving upwards, the drag will try to pull it down. What is that minus 9.81? Is gravity. Okay, so the rest of this kind of ugliness and syntax, it is just like packaging to keep those equations behaving sensibly. That's all it means. If this body is moving upwards, you apply a negative g acceleration and minus the drag. Similarly, if my velocity is down, why would the vertical velocity be downwards? So projectile motion looks like this, right? So when your body is moving upwards, your drag will pull it down. When your body is falling downwards, okay, what happens is gravity will still keep pulling it down because gravity only acts in one direction, but your drag will apply upwards. Okay, so in this case, drag force is kind of acting opposite to gravity. So that is what the if-else loop does. While it is climbing upwards, you apply the force that way, else you apply the force in the opposite way. And that is kind of the entirety of this solution. Okay, there is nothing else in here. That is very difficult. So that's the function. You give the value of time. Time tells you what time step it is at. You give the state vector and you give the drag coefficient. At every time step, you compute the rate of change of the state vector, and that is the output result. Does that make sense? Okay, I want to hear some yeses or some questions. Does that make sense? Yes. Which part? The horizontal, yes, it's the next difference. Yes. What about this? So Z4 is horizontal velocity, dz4 is horizontal acceleration. Horizontal acceleration is minus k times velocity squared. That's all it is. And the if-else thing is only to change the directions. I can write this whole thing in one line of code also, it just becomes a little bit more complicated. Because you take the velocity times the absolute of velocity and solve the thing. Does that make sense? Okay, now can we look at the flowchart? No, the flowchart. Okay. So if you look at this flowchart, what we have done is we have a main script in which we define the parameters of the problem. What is the mass of the projectile? How fast I'm throwing it? What is the angle I'm throwing it at? And we selected the solver. Solvers will get to. You also now understand the last step. You understand from any state that the body is in how to calculate the acceleration on it. Okay. Now this middle portion here, what that ODE solver piece does is it determines the accuracy of your solution or how good your solution is. But actually, if you understand the first script and the last script, you are kind of 90% of the way there. All right. So Euler method, what it does is going between one step to another step, it does it in one shot. It computes a single solution. It's known as a first order method. Runge-Kutta is a fourth order method. It calculates 4 time steps and it gives you a much more accurate solution that will show you. And variable step solvers, what they do is they also change the time steps. So when you're dealing with kind of equations where you want to balance speed of computation versus accuracy, the variable step solvers come into it. And calling the solver is just a matter of syntax. You call Euler method or RK4 method or OD45 method, but underneath it all the dz function will remain exactly the same. Are people kind of getting it? Okay. Shall we have a 10-minute break? Then you come back and like we can go over the rest of it. Yeah. Yes. Okay. Maybe just let's start a 10-minute time limit. Okay. I hope this is making sense. We are trying our best to help make sense. I wonder if we need to simplify one more level.
Yeah.
Yes, sir, freshers.
Hey, PhD.
Yes, sir, PhD. Come with some kind of animation to show this. By word,
Step by
it's,
step.
yeah. Pre PhD research papers related to इसको करना पड़ेगा.
Basics सिखाने.
हाँ वही मतलब बेसिक्स जैसे computations न्यूमेरिकल मेथड्स में जैसे कुछ भी जैसे इक्वेशंस का यूज हुआ वहाँ से शुरू करना पड़ेगा. मतलब रेफरेंस पॉइंट ऑफ रेफरेंस उनको देना पड़ेगा कि रिसर्च में जैसे कोई इक्वेशन है उसको आप कैसे रिप्रेजेंट करें. मोस्ट समझ में आ सकता है.
Just the way where and how it is things. इक्वेशन का रेफरेंस एप्लीकेशन के अंडरस्टैंड अभी ये भी एप्लीकेशन कोई बहुत बड़ा
हाँ गियर
अंदर कब क्या वो फंक्शन कैसे चलता है कैसे सिलेक्ट करना है बॉडी कौन सा बॉडी कब सिलेक्ट करना है दैट इज द प्रॉब्लम.
I want to show you something. Oh, yeah, it's an interesting topic. I wanted to model this using some computation technique, but we couldn't try.
Do that in 6th year.
Oh,
That's Simskip multibody is one of the tools we get. So you can model the gyroscopic effects.
Okay, it's fine. There's one demo also there, I think.
Now I don't know if I'll find it. No, it's not. It's not exactly the same, but it will kind of show you how to get started.
Oh, okay.
I think that example you could probably look at,
Okay,
or this one,
right.
because there are some weird effects that start happening when you get into that stuff. Yeah, but just like look at Simskip multibody because it models the whole 3D thing.
Sure.
Is it making sense, the stuff we're doing?
Yeah.
Some people are lost. We need to simplify. But we lost half the people.
You have to connect, and I think the alternate version of all the
Alternate screens में but on कैसे? Presence of mind shouldn't matter. Anyway, we'll know. Tomorrow we will get. Yeah, I don't know how to turn it on. So if you can draw on this, then it will be easy.
Yeah.
Step by step.
alternate ही बंद करके इसको ऑन कर दो स्क्रीन alternate is that would make sense.
Sorry, that was us. Is maybe we should have a graphic animating at every time step and plotting
Yeah.
and drawing that vector actually. Can you work with Pratyush to do that?
Sure.
Pratyush is good at drawing those vector things. You know this problem. And then you can update that Git repository. So you can download, sync, update this Git. Symbolic wala, I don't think it is needed at the beginning. Because those equations anyway, like E equals U squared 2G, anyway you can put into MATLAB by Symbolic.
Yeah.
Right, so this is how these contents go over time. So the first script we can do purely equations in MATLAB. They will learn MATLAB and the functions also. The function thing you can teach them. And then we can do Euler method plot. And then we can also remove all the density change, and we can remove the density change. Constant density is. No, this is not a touch screen.
Not a touch screen.
Not working, no problem. It's okay. We'll manage. कोई बात नहीं, रहने दो अभी, कल देखेंगे. कल वैसे दूसरे क्लास में.
You can directly draw it around.
हाँ, वो actually distributed है ना class.
कि वहाँ पे अगर ड्रॉप किया तो सब
I think we'll pass that point now. It's okay. It's a learning. Do you want to just go straight to number 3 or do summary?
wrapping it up. Like not going into the
No, not the details, just showing them how the time step changes together.
yeah.
But just check for a summary.
I hope everyone was able to understand how we are using the Euler's method over here, how we are computing Z and then how we are computing dz using Euler's method, and then calculating each time steps. So with that, what we are able to do is this is the plotting part. I'm not getting into that, what exactly it is doing. You can get into the syntax and understand. But what we try to do is from time t equal to 0, with a time step of 0.1, we try to compute each of the next steps, each of the variables in the state variable. And with that, we have the entire information of the problem statement that we are having. So these are again some graphs that came up with the horizontal distance or the vertical distance with respect to time. And these are the graphs of the velocity. So if the drag wouldn't have been there, these actual lines would be a straight line. But because of the drag, there is a variation of that velocity that you can see. Number as it? Yeah, you can. You need to add it. Yeah, you'll have to add that in the code. Whatever changes that you want to do or name them or label them and all, you can do it in the code itself.
Shall we ask people to interpret these plots?
Yeah, maybe. Yes. So what do you understand from these graphs basically? What information that you can pull out of this?
Just zoom in on one at a time. Windows plus.
Yeah, so what is this particular graph? The horizontal distance versus time versus horizontal graph distance. What exactly it is telling you? First of all, just imagine if there wasn't any air drag, how it would look like. It would be a straight line, right? So now what are the changes that you can see over here? Yeah, there is some bend into it, and sorry.
Distance increasing faster.
Exactly. So initially the slope is also variable, right? It's not a constant slope. So what do you infer from that? Where exactly is it faster? Where exactly is it slower? Yeah, exactly. So initially it's going at a faster rate because the velocity is more, right? And the drag, that's why, and uh, as the velocity increases, the drag is increasing, it is pulling it backwards, so it is slowing at a faster pace. And after that, the drag is lesser, and hence the change of velocity is lesser, right? Again, what do you infer from this particular graph? Again, just compare it with the first situation where there was no drag. And what is the difference that you see over here? Yeah. Yeah, this is kind of a skewed parabola. And what more details that you can pull up from this?
Time taken to go to the maximum point and time taken to return from there are different,
Yeah.
not same.
Initially, it is lesser. It goes at the highest point and the quick time.
Velocity was the.
Yeah. The drag velocity is more, so that so it's going faster.
Exactly.
Yeah. And what you can infer from this graph?
Not linear.
Yeah, that's not linear, and
It's not horizontal, because of air drag.
yeah. So again, if it was a non-drag kind of a situation or a vacuum scenario.
Velocity decreases, the drag also decreases, and hence the slope.
Yeah, but how would the equation look like if there was no drag?
Then it would have like a linear straight line.
Straight line, but how?
It is constant.
Constant. So it's a flat line, right? Horizontal line.
Pilot will-
Because the velocity would have been constant. Now the velocity is decreasing. Right? Again, it is decreasing at a faster rate initially because drag is more.
Can I just point out?
Yeah.
Yeah, can I just point out one thing? So, in physics, it's very typical that we like to neglect drag, assume perfect conditions. But just look at those numbers where the horizontal velocity started out, almost like 800, and where it's down to 200. So, if you computed the idealized solution, you won't even be close.
Yeah.
It's like a 4 times difference, 75% difference. So, this is why numerical methods matter.
Yeah.
Because your analytical method would give you 800 and your solution would be nonsense. But once you're able to model these advanced things, that's why we don't like going into this complexity and writing ugly code either. We don't like it. If it was simple, it would be better. However, we don't get the right results. So that's why you have to go into the code. You have to figure out all those conditions. And once you write it, you can see the change immediately, right? It's a very substantial change and that affects all the quality of your results. Thanks.
So with this, And again, if you were to plot the altitude, that is the height versus uh, air density graph, it would look somewhat like this. So you can see that as it was higher, the air density was lower, and as you come down towards the ground, the air density actually increases. So with that, what we did in this particular exercise is we tried to solve this particular problem using the Euler's method, okay, with a fixed time step. So the delta t was equal to 0.1. So we computed at t equal to 0, then we computed at t equal to 0.1, then 0.2, and so on till the last iteration. And then we came up with the entire solution. That is what we did, right? Now, again, previously also I said that when for dealing with such complex systems, what we do is we try to break it into pieces and assume it to be piecewise linear, because for small time step it's almost linear, right? But when we are saying almost linear, there is some limitation to this time step as well, right? Lower the time step, definitely it will give an accurate result because we are going towards linearity there. But then what is the optimum delta t that we can choose? Because ideally it should be very, 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 very small and we can compute the entire solution. But we are also putting a load onto the computational capabilities. That much more iterations we are going to do. So not always we have that computational power of doing unnecessarily very high computations when we can do it at a larger time step as well. So to select that particular time step is also necessary. And that when we are dealing around with fixed step solvers, we will have to do it depending on our application, that what that particular time step is. So what we'll do is we'll try to vary this particular time step. Now the same code, the same way that it has been done, we'll try to do it, but just varying the time step, and we'll see how the error changes. Okay. So it's the same thing. Initially we are setting in some parameters.
Just tell them which step.
Yeah. It's the ML03 Euler error dot MLX. So here what we are doing is initially we are setting in the parameters the way we did previously as well. The only change over here we are doing is we are starting with a time step of 5. That is dt is equal to 5 over here. And the change of that is 0.1. And then what we are doing is we are trying to reduce that delta or that change dt that we had. And for different values of dt, we'll try to compute the same problem that we had. Now, what I'm for as my output or response variable, what I'm trying to compute is the horizontal range that we computed. So what my problem statement over here is, for different time steps, I'm just trying to compute what my horizontal range would be. Okay. And then I'm trying to see how it is changing. So if you look at into this particular graph, so initially we are just looping it around. If you look into this particular part of the code, for different from starting from 1, that is the counter for this. We are just changing dt, and then we are computing the same solver and we are computing the horizontal range for each time step. And this is just used for plotting. So this is the log graph for better better understanding. So I'm just opening it. So as you can see, when the time step is actually decreasing, so on the x variable, here the time step was 5 initially, and then we are decreasing it. Okay. As the time step decreases, the error that we are getting is also decreasing, which is expected, right? Because as we are decreasing the time step, we are making the our lines that we were assuming to be linear, the 2 points that we are assuming to be linear, that is becoming much more smaller, and it's becoming much more linear. And that is the reason we are getting more accurate results. So now, depending on your application, it becomes critical on what is the tolerance for your application. And depending on that particular tolerance, you will actually select what time step you want. Because you also want you want accurate results, but you also want your code to run fast or the computation to happen quick in quick time. So this is actually a trade-off that you will have to decide depending on your applications or your research that you are doing.
I think we probably explain this in also in simpler way. Try that sine wave thing. Were people able to understand this time step thing? Kind of, sort of. Okay, let me show a simpler example. So I'm going to go back to the command window and just show you what we actually mean by time steps and all these things. Okay, so what I'm going to do is I'm going to say t equals 0 to 10. And then I'm going to say y equals sine of t. And then I'm going to say plot p comma y. Okay, very, very simple code. And then this figure pops out. So I said declare a vector from 0 to 10 seconds. Give me the sine value and plot the curve. Maybe I'll put the markers there as well. Okay. Oops. Okay. Does that look like a sine wave? Does that look like a sine wave? No. Why not? What's the problem here? The peaks. The peaks are sharp. Well, one peak is sharp, one is kind of flat. The curve is not very smooth. Why is it not very smooth? Less data points, right? So what I've done is, this is what I'm doing here is a simulation of a sine wave from 0 to 10 seconds. And my step size is 1 second. Okay. So it's like the sine wave is behaving in the real environment. Every 1 second I'm sampling this wave. The output that I get looks nothing like a sine wave. It is approximately that, but this is not what a sine wave looks like actually. Okay, my problem is that my time step is too large. I'm taking 1 whole second before sampling the next value, and it looks quite jagged and it's not very nice. Now, suppose we decrease our time steps and make it 0.1 seconds. Okay, so t equals 0 in steps of 0.1 to 10, and then we do this again. Now look at that. Is that a sine wave? Yeah. It's definitely a closer approximation, right? This is actually pretty good. So in this case, look at the size of the data I've had to compute. Before the size was 1 cross 10 or 1 cross 11. Now what is the size? It's 101. So I have taken 10 times as much data. My curve looks much, much better, right? Let me go one step even further than this. So suppose I go t in steps of 0.01 to 10 seconds. And then I plot this thing again. Now let's look at this. Okay, so that is very, very finely spaced points, and we're getting that nice smooth curve. However, what we are getting here is the size of the data is multiplied by 10 times. Again, but my accuracy has not really gone up because the points are almost still the same. So this is the trade-off that we have to do in computational methods, that we have to select a time step which is good enough to give us reasonable accuracy, but which will not overwhelm our system with too much data. Does that make sense? Any doubts anymore? Okay. So in this case, like the simple sine wave case, what would be a good time step for me? The 0.1 is probably okay, right? Now, if we go back to our problem and we look at the Euler time steps and the error that we are getting. So this is a log plot. The time step here. So this 10 to the 0 is 1. This is 0.9. This is 0.8. Like that, going all the way to 0.1. And this is the error. And you can see error is also in powers of 10. So from this plot, can you kind of tell what would be a reasonable error or a reasonable time step to take? Any ideas? Okay, so the answer is that you actually can't tell from this graph. And it depends, it's very conditional from problem to problem. So if it's a projectile motion problem, okay, and if I'm just throwing a projectile for the sake of throwing it, if I get an error of, I don't know, 10 centimeters, it's probably not a big deal, right? But suppose we are trying to make two spacecraft meet in orbit. I have an error of 10 centimeters. What happens? Is it going to be a problem? Yeah, your spacecraft won't dock. You'll have a mess. Okay. Suppose you're trying to collide two electrons together. Then what happens? So you will have to have a tolerance of 10 to the 12, 10 to the 13, that kind of numbers. So that tolerance is relative to your problem. It depends on what you're trying to do. And this is where the domain knowledge is kind of required for computational methods because you have to pick what the application is. If I'm designing like a car and the brakes have to stop at a particular point, 1 centimeter error is good enough. Like I have never personally designed an engineering system with error less than 1 centimeter. But if you're doing that on a microchip, like everything's a mess. So it depends. Next, what we're going to show you is like how you can choose a higher order method and that consistently gives you less error across the board. Okay, so that's known as the Rangekata method.
So in Euler's method, basically what we are doing is we had that time t equal to at one time step, we computed, we had the dz value, and then we went on to the next value. That's it. But when we go into the higher orders, like the Rangekata methods, we are trying to compute intermediate points, and depending on that, we calculate the value of y the next time step. So that definitely is adding to some computations. It is definitely more computations, but it's also giving more result, more accuracy because you are actually considering the intermediate values. Okay. So I hope everyone is aware what exactly Rangekata formulas are. So basically, it takes in the intermediate two values and then computes the next step. So for that, I'll be using the ML04 script. It's again the same steps that we are doing. It's similar to the ML02 where we used it for Eulers. Entire steps are same. The only difference that I'm doing over here is I'm selecting a different solver. So the solver over here is 2, which is for Rangekata method. That's the only difference that is there in this particular script. So I'll just run through the entire script at once. So this graph actually tells you how the next steps are computed. There are 4 variables that we are computing: K1, K2, K3, and K4. 2 of them are at the center of the time step that we are taking, and that is helping us to get a more accurate output at T0 plus H. So again, we have calculated the same parameters and we are doing exactly the same steps. So in this particular part, you won't be able to understand what exactly are the changes. But what we'll do is we'll try to calculate the errors for Rangekata as well. And then we'll compare between the two solvers that we used. Anyone wants to understand or have more information on how exactly is the Rangekutta working internally?
Yeah, that figure will show actually. You want me to? Okay. So we will not do the whole derivation or anything like that. We'll just tell you how it works. You can assume like these smart people, Range and Kata, they came up with this method, and it gives you better results. We'll show you that. Let me just very quickly draw you the thing in Paint or something, so you understand what it means. Okay. So just forgive my drawing skills, however they are. So suppose that this is a kind of a curve that we're trying to compute a solution over. Okay. Now suppose my starting point is over here where I draw the red dot. Okay. Now if I'm here and I know the gradient is kind of this way, how does an Euler method solution work? Okay, so what you do is you basically take a time step, right? So you call this time step something like dt. And you assume that that gradient is constant for that time step. And then you generate a solution. So it's basically like a straight line, or it would look more like this. And you end up with a solution somewhere over here. Okay. So if you use Euler method on a curve that's changing, you stand at any one point and you look at the gradient, you walk that far ahead in time, and then you estimate a value. What is the problem here? It might not always be on the what? It might not always be on the curve. Okay. So this orange line that I'm drawing, that is the difference between the actual solution and the computed solution. Yeah. So that is the computational error which will happen with almost any method. How do you reduce that error in Euler method? Smaller time steps, right? So you reduce the size of dt, automatically that difference will minimize. You can see that visually, right? What Rangekutta method tries to do is something quite clever. So I don't know if I'll be able to do justice to it in like a couple of minutes, but what it does is it computes solutions at 4 points. So instead of taking that jump in one step, it takes 4 steps, the fourth order Rangekutta method. So it will compute a solution kind of at the halfway point, 2 different solutions, and at the end point, and then it will take a weighted average of those solutions. So what you get is a smoother match to the curve, whatever it is changing. And what that allows you to do is even over longer time steps, the error with the curve is much smaller. Okay. So what that looks like, again, we have put a kind of a graph here. That's what it looks like. So on this graph, that blue line is the actual function. Okay. And we are starting at a point y naught. So what you do is you start at a point y naught, and then you compute a solution using the gradient there, which is called K2. And then you compute another solution K3, and using those you compute another solution K4. So you compute 4 points, and then you take a kind of weighted average of those 4 points, which allows you to get somewhere very, very close to the actual value of the curve. You can see that if we just took K1, we would end up down here somewhere. But the Rangekutta solution is kind of up here. Okay, so that's how it works. It basically tries to fit to the curve. The actual equation is given in the scripts for you. We will not go through the whole detail, but if you open this function, it's called one-step Rangekata. That is the actual maths that's behind it. I can zoom out. Okay. So the first solution is just at time step. Sorry, it's at a time of t, which is the first point. The second solution is computed at a time of t by 2. The third solution is computed using the value in the second solution. Okay, so you will see a by 2 over here, but you will see b by 2 over here. And the fourth solution, d, is computed at the full time step plus the value from the third one. So it is trying to kind of converge on the correct one. And what you do is you take a weighted average of these four values, a, b, c, d, like this. So z equals z plus a plus 2b plus 2c plus d by 6. Before it was just z plus dz by times time. Okay. The maths behind this paper, you can go and read the maths behind this, you can read in the original paper, but that's the code of how the Rangekata fourth order method works. Make sense? Okay. Now, maybe we can just show you what the error looks like.
Yeah.
Okay. Yeah. Okay. So running it is exactly the same as everything. The scripts are set up in a way that you just change solver from 1 to 2. It will automatically start using Rangekata method. And when we show you the errors, again, we're not going through all the steps. But when we run the script ML05RK error, okay, what you will see is that Rangekata method is much better at giving you consistently low errors, even at larger time steps. So if you scroll all the way down, this is the plot we get. And this is a comparison of the Rangekata method versus the Euler method here. So what you will see is at the extremely small time step, 0.1 second, Euler and Rangekata give you actually the same answer. That's the best answer. Okay. However, if you multiply the time step by 10 times, the Euler method error goes up by factor of, it's almost 2 orders of magnitude. But the Rangekata error stays quite low. Same thing, even if you raise the time step even further. The error in Euler method climbs very high, but Rangekata stays low. Okay. So it is just a more stable method. Yeah. Yeah, we were actually wondering about this experimentally. Why is this the case? So the way we are calculating the error is we are measuring the difference between the final endpoint of the smallest time step. Okay. The reason I think they are changing so much is whether a time step is an exact multiple. Because what is happening is we are stopping our solution when your projectile goes below the 0 line. Okay, so your projectile is falling. Suppose this is the 0 surface. As soon as it goes below the surface, you stop the simulation. But how far below has it gone before you realize to stop it? That this simulation is probably not sure. Because suppose your projectile was here, okay, and your next time step brings it here, your error will be quite large. Okay, but if your projectile was here and you end up just here, then you will get quite a small error.
So Euler, it was already sure that if the final point was already. I mean, why is this like the Euler method? Even if the Euler also it would have been dispersed after specific names.
No, because in Euler method, you realize the magnitude is much larger. So the noise gets cancelled out. Okay, so you have some error here, which is a kind of a boundary where the simulation stops. It's like a band. So that error itself is so small in the case of Rangekata that you're confusing it with the actual signal. Euler method is 100 times larger error. So we lose the signal in the noise, basically. Okay, that is my suspicion. I am not 100% sure about this answer. I'm just trying to interpret the results that way. Okay, makes sense? All right. When is the stopping time for this? Just wondering what I want to show you. 6:30. Do you want to carry on or shall I do the beginning? Very well still. All right. So this is typically how far people get in their numerical methods courses. However, we want to show you some like even more advanced stuff compared to this. So if you look at your script number 4, which is the shoot RK method, I'll just close the rest because they're not needed now. So if you just open script number 4, what you can see here somewhere. Okay, no, you actually can't see it. All right. I'll just try to explain it manually. Okay, so even in the Rangekata method, one problem what you have is that the time step is constant. So suppose this XY trajectory is there. Even when I'm computing this trajectory, I know that this curve is quite flat in this region, right? And I know the curve is quite flat in this region, but the solution is changing fast over here. So Rangekata method, you can use larger time steps. However, it is still computationally inefficient because it's a fixed time step. So for generating this solution, you have to do around 300 to 400 calculations. Let me just run it and double check that number for you. So if I look at the value of time, the output time that I have, this is around 710 time steps that we have to use to generate this curve at an error rate that we are comfortable with. Okay. One more innovation that happens beyond this point, what you can do is you can change the time step also using some algorithm. And that algorithm is quite interesting. So those are known as variable time step methods. Has anyone used the OD45 solver inside MATLAB? Has anyone heard of it?
Yeah, heard.
Okay. So in the next script, we're just trying to tell you how it works, more or less. If you want to go into the details of the code, everything is here. Okay. So I'll just try to explain what we do. And then I'll show you how we do it. The script that does this is ML06 var solver. Okay. Let me look at what graph I had. All right. So I'll try to draw it out for you. If this thing was working, we would have tried that, but it's okay. Okay. Now imagine I have a curve that looks kind of like this. That's what my velocity curve looks like. And I have to compute solutions at different points. Okay. Now the interesting thing is if I was standing here and I computed the gradient going that direction, I could walk almost all this way before my error increased. I could get almost here, right? Because it's almost like a flat thing. If it's flat, the gradient is not changing. I can, in a single time step, I can jump there and not have to compute every small point like here, 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 every single point. Okay, and Rangekata method is costly because for every point you have to compute 4 subpoints below it. Okay, so something interesting was kind of discovered from fundamental maths that when you change the order of your solver, the error also changes. So like we went from first order to fourth order, our error changed quite a lot, right? The reason this happens is mathematically interesting. I'll just show you. There's a small script here. If you open this script called Taylor series demo inside your folder here. Okay, it says Taylor series demo.mlx. It will actually show you exactly what is happening. Does everyone understand what Taylor series is? Okay, so you can decompose any mathematical function into some polynomials with different coefficients, right? So suppose that we are looking at a function like, let's say, sine x. So what you have to do is you have to run the codes in line 10 to 14 and then you change parts of it. So if I'm looking at a function like sine x and I'm computing a second order solution, that solution looks like this. Okay, so suppose sine x is the function, we expand the Taylor series, we only use the first two terms. It gives us like this line. So what you can see right in the vicinity of where we have selected that point, this generated solution matches the curve, right? But as you get far away, it diverges. Same thing we saw in that plot right now. Now what happens is, suppose you go to a higher order method, let's say fourth order. Your solution matches over a larger range, as you can see here. And it also flips. So you had a straight line, now it looks itself like a polynomial. Okay, suppose we go to one more higher order method. We change this to, what was I changing? We change this to 6. Okay. Again, you will see the direction that those things are diverging in change. So initially the line was like this with a positive slope. Then your algorithm flipped the slope of your polynomial. Again, you increase the order. Again, the sign is flipped. Okay. So what happens mathematically? There is something very interesting going on, which I don't know enough maths to explain the backend, but we kind of observe this. Suppose I compute a fourth order solution starting from this point here. Okay. The fourth order solution, suppose it ends up kind of here. Now, if I compute a fifth order solution, it will end up approximately kind of here. It will be closer to that thing. So if I compute these two solutions, I can give them some names. I can get the error between these two. So I get the error E. Remember that when we are trying to solve for a real function, that black line is not visible to us. Okay, we don't know what the system is doing. We have to compute it. So instead of jumping forward to any time step, what you do is you compute a fourth order solution and you compute a fifth order solution at the same time. You decide, is the error larger than your tolerance allows for? If the error is larger, then you shrink your time step. And if your error is small enough, then you can expand your time step. And what that allows you to do is dynamically, it allows you to flex your time step. Yes, there are questions. Yeah.
Like the example that you showed, sine x is like sine x has a large.
Yeah.
So x square has order. So
Yeah.
we go to the order. So if there's a function like say of order 6, and we are computing and we try to approximate. So our tangent, a normal with an order of 5 and a normal with an order of 7. That you are saying. But if we go beyond, you said that higher orders are closer. So if we go beyond like order 8 or 9, would it give closer results or farther?
Okay, so the question is, as we go to higher orders onwards, does the error decrease?
If the order of the function in question is
Yes.
finite, like 6. So, and we are going beyond that.
I think it should, because your function iteratively gets closer and closer fits. That's what the Taylor series does. Okay, so as a rule of thumb, again, there might be exceptions, I don't know. But as a rule of thumb, the higher order your solution is, the closer the fit is typically. So, but the flip side is the higher order your function is, the more terms you have to compute, your cost of computation grows. So that is why people have, through experimentation, they have settled on this method, the fourth and fifth order method, which becomes OD45, which is the default one used in MATLAB. However, you can use different types of solvers. There are OD113 solver is also there in MATLAB, or OD15S is also there.
That responds to 113 or
No, it's 1 and 13. Okay, so these are all kind of methods that have been figured out with trial and error. So 45 gives you good solutions. There are also other ones. If you want to see the list, you can go and see the list through the documentation. So if you just go to your MATLAB command window and you type doc ODE solvers, okay, it will give you a complete list of the different solvers which are there. So there's a page called choose an ODE solver. And there's a list here. These are all the different kinds of orders of solvers which are there. So you can see OD45, OD23, OD113, 7, 8, 8, 9. And there are stiff solvers as well, which I'll show you an example of. And there are also implicit solvers which do something different. Okay, so if you want to learn about any of them, you just click on the link, it will show you the documentation. And it will reference the paper where it's come from. Does that answer your question? Any more questions?
so what
Yes.
is E, like your error, what exactly is like between the error between 4 and 5?
Yes. So what you're doing is you want to get close to that black line, but you don't know where that black line is. Okay, so what you do is you compute a fourth order solution and a fifth order solution. If the difference between them is large, difference is error, then you need to reduce your time step. Otherwise, you can expand your time step and you can compute this thing much faster. Does that make sense?
Yes.
Is this all getting a bit too abstract, or it's okay? Okay, you all are still here, so I'm assuming you're following. Right. So again, I don't necessarily want to go into the full code, but I'll tell you how it works. So in this case, it's exactly the same type of script, but instead of calling that function OD solver, we call that function OD solver var. This is the variable step solver. And the way it works is very simple in principle. So you compute a solution using the fourth order Rangekata method, and then you compute a solution using the fifth order method. If the difference between the two is greater than your tolerance for error, then you squeeze your time step. Otherwise, you expand your time step and then compute the next solution. Okay. If you want to use this code for yourself, you can open this ODE solver var function. And inside here is given the code of how the time step is adjusted. That's the code. So what we do is we compute one solution using fourth order method, another solution using fifth order method. We get the error between them divided by time step. And then we've just put in some value of 0.1. And then we increment, or we change the time step increment using this equation here. So if the error, so the error here is actually Q, not E. So if the value of Q is small, which means your error is small, your time step will increase, otherwise it will decrease. Okay. And if you run this, so if you run this ML06 shoot var solver, we've made a plot here of how your time step dt is changing. So until now we had a fixed time step, right? We put our fixed time step as 0.1 or something like that. what you see is as the number of time steps go on, the value of dt itself is changing. So at the initial part where the velocity is high and the drag force is acting very rapidly, we choose a very, very small time step of 0.05, even smaller than what we had specified. However, once it enters into that predictable region, then the value of your time step climbs and it goes above 0.3. So in total, what happens is the number of steps you have to compute is only like 350. Whereas in the previous one, you had to do, I think, 700 plus calculations. So it becomes more efficient. Okay. Yeah. Its efficiency depends on what the function is. Yes. So that's the next thing we'll show you. After one more thing. Does everyone kind of follow? So if you want to use any of this code, right, the reason we have structured this code this way, for your problem, all you have to do is rewrite that dz function. The rest of the solvers will actually work for you straight away. That's why our code is a little bit more complicated than what it might be if you just wrote it yourself. Because you only have to change the dz function for your problem. Otherwise, the rest of the script you can use entirely. Okay. So this is something that I kind of wrote manually when I was doing my master's degree. How does this compare to the MathWorks built-in solver? I wrote it just for kind of fun, just for checking. So in this ML07 script, we are using the built-in MATLAB function, which is OD45. This is a fourth and fifth order solver. When I ran this script, I found that, oh, by the way, I put in a relative tolerance of 1 e to the minus 9. Okay, so I'm demanding a much higher accuracy than that 0.1. It's your best guess. Yeah. So by default, your absolute tolerance is 1 into the minus 6 in MATLAB. You can define what you want. If you're working on some particle physics stuff, it has to be smaller. If you're working on like automotive stuff, it can be larger. Okay. So I just ran OD45 and I found out that the MathWorks official solver does something more interesting than even my script was doing. And it changes the time step all the way from 0.05 up to 0.55, but it also has these sharp drops in the time step, and it does them in chunks of like 4 seconds. 4 steps. So the OD45 solver inside MATLAB computes 4 points and then decides whether to go up or down in the time step. And just experimentally, what we found is it's like even 50% more efficient than the code I had written. So if you want to use the built-in solvers for your problems, I think they will give you a more efficient solution. Okay, so if you just used fixed step Rangekata method, you had 750 steps. If you use the 45 method that I have shown you the code for, that gave you around 350 steps. And the inbuilt solver that is supplied with MATLAB, that computes it in about 270 steps or so. So you're getting quite efficient at that point. If you want to learn how to write equations using OD45, this script has all the format, like how you write the functions. And I'll also show you where the official training is. So what you do is you just go to a browser and type MATLAB Academy. Okay. And you should be able to find your way to this page here. So it's matlabacademy.mathworks.com, and it will say self-paced online courses here. And this you can also share the link with all the participants of this workshop. Now, if you want to learn how to do maths, you go to the left side and click on math and optimization. Okay, and inside here, there are all these courses which are for different types of mathematics. So introduction to linear algebra, solving ODEs, solving nonlinear equations, and symbolic maths. So solving ODEs, this course actually teaches you how to use OD45 in a proper way. The stuff that we have shown you is a little bit outside of this course. So if you want to do this course for some extra practice, you can. And then you'll also get a certificate if you complete all the exercises. So if you want to learn how to use these solvers for your problems, like this will teach you how to solve ODEs numerically, how to write the function, and then how to solve systems of ODEs, and then how to solve higher order ODEs. So it will teach you, suppose you have a, let's say 13th order system or 15th order system, you can actually break that down into 15 first order systems. There's a method of doing that using the state space methods. And that allows you to rewrite a higher order system as a system of smaller first order equations. And that way you can crunch through these numbers. So just go and take a look at this course. It's self-paced, so you can do that in your own time. This is like matlabacademy.mathworks.com. You can just save this page also. Okay. Almost the final thing we wanted to show you today. First of all, are there any questions on this OD45 piece? Or variable step in general?
So can we use different like RK4 or RK2 method or some other method in the same for the same function? Because if we know, say, the function is very much predictable in a certain region, then there's no point using RK4 in it, right? Like steady space. Even if we reduce the time ATM, even then we are actually involving a lot of space because of RK4.
Or it will be actually change the solver itself in the middle.
Within the
Not with anything that we supply. Okay, so MathWorks official solvers won't do that, but you can write your own function. But you will have to use the same method, I think, almost.
the method would be more or less similar to the variable method.
Yeah, so you can have variable solvers, but accuracy, like we will not guarantee that. So OD45, we have certain checks that we guarantee certain accuracy for this, provided you write your problem. But if you're changing solvers in the middle, the behavior is unpredictable. Like we don't know what to do. So you can try it out. All right. Everyone with us so far? Let me show you just one final thing about where even this stuff fails and where you have to go do some different things. So the last script that we have in here is called ML08 solve stiff ODEs. Okay. And this is again the place where people get really badly stuck. And when you tell them the solution, it's just like an instant thing. So first of all, what is a stiff ODE? So if you take an equation of this form, this is known as the Van der Pol oscillator. Okay, it looks kind of simple, but what you do is when you increase the value of this variable mu, this function becomes very, very sharp at certain points. Okay, so that's what it looks like. Sorry, I'll just show you the. I have to run the script. I'll show you what the shape looks like. If you run this on MATLAB online, it might take quite a long while. So this is what the shape of the Van der Pol equation looks like when mu is equal to 1,000. So when the value of mu is low, this function is almost kind of smooth at this point. But as your value of mu becomes larger, this becomes very, very sharp, almost coming to a point until it becomes, this is basically like a discontinuous function at that point. Okay. So what happens is in the case of systems like this, which sharply change at some point, even your OD45 kind of solvers break down. Because what will happen is, suppose I go into this point and I look closely at the time steps. I zoom in here. So you will see this part is behaving as expected because your time steps are getting shorter and shorter and shorter, coming closer. But as you keep zooming in here, It's almost like a fractal. I mean, you can keep zooming in. And this is what's happening to the time step. So it squeezes to a very, very, very tiny value, and then it has to expand again from that value. So if you have a kind of system which is stiff in this way, sometimes you have a spring which has a backstop here. So it's like, suspension of a car, where if you're just bouncing on a spring, solving that problem is easy. But if you suddenly hit the ground, that's like a stiff system because your contact forces are very difficult to model. Okay. So in that case, you have to use something called stiff solvers, and I'll just show you what the difference is. If I use OD45 to solve this kind of problem, the number of time steps it is taking is this number here. Okay, so that's what 1,000,000,000. It's like 6.7 million time steps to solve that shape, which looks kind of simple to us, but it is complicated because at that point, all the time steps get squeezed together. One simple fix to this is you switch over to using something known as a stiff solver. The details I won't go into. But stiff solvers typically are named like this. So they will be OD15 and then they will have an S at the end. That stands for stiff. Okay. And if you use OD15S for the same problem, what will happen is your number of time steps reduces quite drastically. You can compute exactly the same problem in just 592 time steps. So what is the savings? It is almost 11,000 times more computationally efficient.
Just took a lot of steps.
Yes, yes. Yeah, so for a value of mu equals 1,000, it took 6.7 million steps instead of 500 something. If you increase the value of mu again, make it 2,000, the number of steps will rapidly go to infinity because that point will become sharper and sharper. Okay, but the stiff solvers don't really care about that because they're able to adjust more easily, but they're also more computationally intensive for each time step. So, I mean, here we are kind of, there is no hard scientific method to prove what will work best. So we're just showing you different options because different problems have to be solved in different ways. And just by picking the right method of solution, you can become 10,000 times more efficient. And you might be able to, crunch your way through very, very large systems if you just use the right method. So how to find which solver to use? You just type doc ODE solver, like I just showed you. And you open this page, choose an ODE solver, and here it will actually give you all the details of all the different types of solvers there are. Okay. There is this table here, which lists all the solvers which are in MATLAB. It will tell you what type of problem it can solve, what is the accuracy, and when to use it. And then you can just click on the documentation, and that will give you a description of like how it works properly. And if you hit examples, like it will give you examples of how to use different kinds of equations. So what we've done today is we've shown you the simplest possible problem that we could choose. It's just like projectile motion with a little bit of air resistance. This one here is more interesting. So this is like a baton that's tossed into the air. Baton is like a stick. Okay, so if you toss a stick into the air, it has those XY coordinates, but it also has a roll. It rolls in the air. So you need different kinds of methods to solve that. There are like predator-prey equations, which happens when one system is feeding upon the other system. So they're dependent systems. You can just go and look at the examples if you want more problems to look at. This one is about celestial mechanics. So a full kind of solar system of stars with multiple stars is simulated here. I think they're talking about the Pleiades, which has like 5 stars. And there's like a stiff transistor problem. There's a there's a bunch of them. Okay, so we hope we've been able to give you an overview of how solving ODEs works. If you want more examples, just open any of these and study these in detail, and you will kind of understand how they work. And when you go through 2, 3, 4, 5 problems, that understanding rapidly builds up, and then you'll be able to solve these on your own and do that training course as well that we talked about. Okay. Shall we end here today, or what's the thing? Okay. All right. Let me just show you a sample of what we'll do tomorrow. You can just look at the pretty pictures. So tomorrow we'll show you how FFTs work, which is fast Fourier transforms, which is gaining an understanding of how repeatable signals work. We'll also talk about partial differential equations. So let me just run the demo like you'll be able to see. So if you have a equation that is two-dimensional, that looks like a wave like this. What you have to use to solve this is like an ODE, but that's a partial differential equation because the change depends on space as well as time. So it's multiple variables changing together. So we can solve that kind of problem also. We'll look at this one tomorrow. General research discussions, like we can have that as well. We can show you how to speed up code, how to write better code, things like that. Okay, cool. Will we wrap up? Anything else? Okay, anything else, or can we wrap up for the day?
Will you cover PDE with boundary condition?
About that. So if you look at that, when the wave reaches the edge of the domain, it reflects that. Right, so that's a PDE that has some boundary conditions. So we can cover that kind of problem. All right, great, thanks. The details of the venue and stuff, we don't know, like your organizers will tell you. Great, thanks everyone. Have a good evening. I'll just stop the recording also.